Now that we've established a basis of Newton's first law, it's time to move into Newton's second law. Newton's second law is probably the most important of the three laws that you will learn in Physics 20, also because it's going to be the law that you're going to use significantly throughout this course and Physics 30. So we're actually going to spend a significant amount of time on it. So before we get into Newton's second law, we're just going to kind of look at this from a little of just a grander standpoint, just kind of to understand the gist of what's going on. So we're going to look at an object, and we're going to say that it's accelerating with some acceleration a. Now, if we want to increase or decrease that magnitude of the acceleration, we could change the net force acting on the object. And we kind of know from science 10, and even just general intuition, if you increase that net force, you're going to increase the acceleration. But if you decrease that net force, you're going to decrease the acceleration. What we can get from that is we can get that the acceleration is directly proportional to the net force. So if F net goes up, A is going to go up, and consequently, if F net goes down, A is also going to go down. So if we were to kind of plot this type of relationship, A is a function of F, it's going to be a linear relationship, just because they are directly proportional. And this is nothing new. This is something you would already know without having taken a physics course. If you give a harder push to something, it's going to have a greater acceleration. If you give a light feather touch, it's going to have a small acceleration. Now we can also just look at the case. Let's say we have the net force, this force that we're applying on the object. Let's keep that constant. Let's vary the mass. Now if we have something that has a very light mass, kind of from Newton's first law, we talked about things that have a lighter mass, they're easier to accelerate. So with a constant force, if we have a lighter mass, we're going to have a larger acceleration. But if we have a larger mass, this object's going to have more inertia. It's going to be much more difficult to accelerate. So this is going to have a smaller acceleration. Now what we could say in this case is we could say that the acceleration is inversely proportional to the mass. What this means is that if the mass goes up, acceleration goes down, and vice versa. If mass goes up, if mass goes down, acceleration is going to go up. And we can use this idea again for plotting purposes. You know, if I was to plot acceleration as a function of mass, we're going to have this nice inverse curve here. So knowing these two ideas, that the acceleration is directly proportional to the net force and the acceleration is also inversely proportional to the mass, we could combine these two ideas together and we could get this relationship that the acceleration is proportional to the net force divided by m. Now this is what we would call a proportionality. We can't say A equals this unless we determine this thing called the constant of proportionality. Like we have to see, how is A equal to the right side? Like, do we have to modify this F net over m? Do we have to have some multiplicative constant in front of it? Well, to cut to the chase, just because it's not overly important, without proof, we're going to find that that constant of proportionality is exactly 1. And if you don't understand why that is, don't worry. It's not actually a big deal for the purposes of Physics 20. What we're going to get is we're going to get that the acceleration is equal to the net force divided by m. This is Newton's second law. This is how it's presented on the data sheet. What you're more likely going to see it as is this F net equals ma. This is the more common form. You'll see it in Physics 20 and 30. This is what I would say is the more useful form. So we have F net is our net force in newtons. M is the mass in kilograms. And A is our acceleration in meters per second squared. Out of everything you'll learn in high school physics, this is probably one of the most important things that you will learn. It's a very small formula, but it's incredibly powerful, and what we want to look at over the next little while is how to use its power. Now earlier I had mentioned, we talked about the definition of the Newton being a kilogram meters per second squared, and I said if you kind of were like, how did you get that? I said, I'll show you later. Here's the later part. Now, looking at the formula F net equals ma, I know the net force should be in units of newtons. I have my units of mass, which is going to be a kilogram, and I have my units of acceleration, which is meters per second squared. This is how we get the Newton is a kilogram meters per second squared. we just use this equation here to derive that. And anytime you're asked to break down units, find a formula that has that unit in it, and then you substitute the units for the other variables in the equation. That will help you break it down into sort of its fundamental units. Now, with Newton's second law, there's a few key important points. The first one is that this assumes that mass is constant. So if the mass is changing, Fnet equals ma is not going to be useful to us. So if you're talking about like a rocket that's burning fuel, we couldn't actually use that. That is also beyond the scope of high school, so don't worry about it. The derivation also assumes that the acceleration is constant. If the acceleration is changing, we can't use Fnet equals ma. Again, outside the scope of high school, you'll need some calculus to do that. The big thing with using Fnet equals ma, though, is that word net. This applies to the net force. So what we're looking at is we're accounting for all the forces acting on the object. That total of the forces, that is equal to the mass times the acceleration of the object. But this key point here, 3, that's something we're going to explore a lot in depth. When you take Physics 30, you'll actually learn that Fnet equals ma, it's not actually the way that Newton had proposed his second law. He actually expressed it in terms of this quantity called momentum, but that's something you can save for Physics 30.